Any questions? All right, so we've gotten some of the vocabulary down on waves. So let's talk about the types of waves, or mechanical waves more specifically. So there are two main types of mechanical waves, longitudinal and transverse. Now what I mean by mechanical waves is that in order for the wave to actually move from one place to another, it requires an actual medium. There needs to be some material that is moving, that is vibrating some particular direction. So mechanical waves requires a medium, which is, again, just a material which has particles in it. So the longitudinal wave, the particles will travel parallel or anti-parallel to the wave. So an example of that, we can demonstrate with a slinky. Actually, I've been demonstrating longitudinal waves since August, but you didn't necessarily recognize it as such. So if I take a slinky here, let's get a little bit more to it. What I'm going to do is I'm going to release some of the coils at the top. And I want you to sort of observe, there should be a pulse that sort of shoots all the way down and then back up some. Did you see something falling all the way down to the bottom and then sort of bounce back up? That's a longitudinal wave. Because the actual particles, in this case the coils themselves, all they do is they just move a little bit. There's nothing physically, there's no coil that moves all the way down to the bottom. It's just that there's a place where the coils are closer together and that propagates down. But the particles themselves, the coils, just move just a little bit. Transverse wave, the particles in the medium. Particles will move. I'll have to word out there. The particles move perpendicular to the wave. Now this is easily demonstrated with this group. We're going to do a fan wave, stadium wave. So what's going to happen is you two are going to stand up and then sit down. You can feel free to throw your arms up if you wish. And then when they do that, the next group, as soon as you see them do that, you do it, and then you guys will be up and down, and then you'll be up and down at the end. All right, here we go. Whenever you two are ready. Why don't you synchronize it? All right. The wave moved that way, but the particles, you yourselves, just moved up and down. So you're moving this way while the wave is moving that way. So you're moving perpendicular to the wave itself. So that was a transverse wave. So I'm going to just call this a slinky pulse up here as an example. And then the transverse wave, I guess stadium wave? No, it's more than just these two. Another example of longitudinal wave, why I said I've actually been demonstrating a longitudinal wave since August with you, sound is a longitudinal wave. What's happening is that my vocal cords are vibrating back and forth, and it pushes air in one direction, and that air will hit another bit of air, which hits more air, which hits more air. The air coming out of my throat is not actually hitting you in the ear. It's hitting something else, and those particles are bouncing backwards because it's a collision. But the next particles will hit something else and bounce back. So the particles are just moving a little bit till they hit something else, which transmits the sound, which hits another particle, which hits another particle, and eventually hits your eardrum. Besides the stadium wave, a transverse wave, an example, I'm just going to write down long coil. And what I mean by that is a long coil. And that's about a third of it right there. And so I can put a pulse into it. Let it calm down some. We'll demonstrate this one better in the hallway. I'm going to put a little pulse in it, and it basically sends something down to that end and then bounce backwards. We will have a much better demonstration of this in the hallway, which probably will not be picked up on the camera, but so it goes. And then in geology, you have the P waves and the S waves. So those people who study earthquakes will be somewhat familiar with P waves and S waves. So the P wave, P stands for one of two things, and I haven't really nailed that down yet. It seems to be, it could stand for either of them. It stands for primary and stands for pressure, or. Whereas S could stand for secondary or shear. And shear or shear, the geology people I talk to are vague on this. So if we have an earthquake here, so an earthquake at this part of the world, and then we're over here, we have our little seismograph. So I have something that's rolling around and track marks that are being left in it. There are two types of waves that are being created when an earthquake happens. We have longitudinal and transverse waves. Well, if we think about it, longitudinal waves require one particle to smack into another one, which smacks into another one, which smacks into another one. And so longitudinal waves can actually travel through solids, liquids, and gases. The fact that you can hear me does indicate that since sound is a longitudinal wave, longitudinal waves can travel through gas. They can travel through solid. If I tap on this end of the desk here, that end of the desk over there moved. Transverse waves do not work particularly well in liquids and gases. So let's give a demonstration here of how well a transverse wave will affect you. What I'm going to do is I'm going to take the molecules of air in front of me and I'm going to drag them in one direction and see how long it takes for them to for you to feel it. Did you feel that pulse? Did you feel yourself getting pulled off to the side? Occasionally I have sensitive students who claim to feel it. But the fact that when I move the air molecules this way, they're not pulling other air molecules with it. So I've got this right here. When this part of the coil goes up, it drags up the next part of the coil along with it. When I come back down, it drags the next part of the coil with it. Transverse waves require, it's a pulling on the next part of the medium, which creates the transverse. They're not bumping into each other, they're pulling on each other. So the first waves to hit here are the primary waves, the longitudinal ones. They're just going straight through the Earth. The transverse waves travel around the side, along the crust. And then you take into account distance and figure out how long it would take. And this is some of the big evidence, the fact that the middle of the Earth is not solid. That there is something, liquid and plasma in here, which transverse waves just can't travel through. And then with enough earthquakes and enough calculations, you eventually figure out how big the crust is. So, we're near the end of my geology knowledge. Not quite there yet, but almost. I have yet to mock the term subparallel. So those are the two types. Now, how do we actually represent this? Well, if a transverse wave is easy to represent, since it's physically, you have something moving up, pulling something along with it. So if I'm drawing a transverse wave, we can look at the side of it. This would be a representation of a transverse wave. A longitudinal wave is a little bit different because we have one thing bumping into another. So if I had sound transmitted, I could draw it with a series of dots here, representing the molecules really close to each other, and then they're less close. And then you get a point where they're really close again, and then less close. Or in the case of the slinky, we've got coils really close to each other, and then coils not so close to each other, and then coils close to each other, not so close, really close. This is not necessarily easy to draw up on the board, so we need another way of drawing this. And the way that I would draw this for a longitudinal wave is I would use basically something that kind of looks like that. Where peaking, where I've got them really close to each other, and troughing where they're farther apart, peaking, troughing, peaking. And so this is a longitudinal wave, but it's not a physical representation of the actual shape of it. It's a physical representation of where you have high density and low density. These places of high density, this is known as compression, and the low density, this is known as rarefaction. And I've always heard it pronounced not rarefaction, but rarefaction. I think there was a test question a couple of years ago about longitudinal waves. And the answer was that it was made of compression and rarefaction, as opposed to transverse waves. Questions up to here? All right, let's head out into the hallway, do some demonstrations, do some transverse wave stuff. I will need a volunteer. All right, so hold here still, I'm just going to set up a wave down. Transverse wave, because the coils are moving perpendicular to the actual wave movement. So the first question is, what happens when the wave reaches Carrie's hand? Okay? How does it bounce back? Not in mechanics, but physically, what are you seeing on the reflection? Okay, part of that is it's dragging on the floor. So in a nice ideal situation, all the more problems, they would not be getting smaller like that. But on which side am I sending the pulse?
The right side.
And okay, so I guess your right. No, my right. I'm saying my right. And then the reflection. Yeah. So with the fact that she's holding the still right there, that is known as a fixed end. So when a wave hits a fixed end, it will reflect, but it will reflect on the opposite side. Basically gets inverted. So now if you can spread that rod through the loop at the end. And then put your hands farther apart. Okay. So that is a free end because the end can move. So what I'm going to do is probably just hold it just a little bit off the ground. I'm going to send a wave through. Now look at the reflection this time. On which side was the reflection that time? I saw people demonstrating with their hands. It is on the same side for those who missed it. So when a wave hits a free end, when the wave hits a free end, it will reflect, but it will reflect on the same side. It's not inverted. Later. All right, that's it for the rod. So I take it off the rod. All right. So now, what I'm going to do, I'm going to send a pulse down. Carrie, I need you to send the pulse back at me at the same time. We're going to send pulses towards each other. All right. So I'm going to 3, 2, 1 pulse, and when we do, both go out to about here. So it was this 3, 2, 1 pulse like that. 3, 2, 1 pulse. So the question
question is, what happens when the waves meet? Okay. Bigger than what we said? Alright, so we're sitting out about this far. Okay, so 3, 2, 1, pulse. Okay. So the fact that when they met each other, they created something bigger. This is known as constructive interference. Now send on opposite sides. So I'll do this side, you do that side. 3, 2, 1, pulse. What happens when they met this time? We'll do it again. 3, 2, 1, pulse. Okay. Did it create a bigger wave than what we started with? So I got a no, a slightly, and a little. It made a little wave or made it a little bit bigger? Okay, it moved a little bit. All right, let's do it one more time. 3, 2, 1, pulse. Huh. All right. Twice. One more time. So how far are you going out? Okay, it's about the same there. All right, so 3, 2, 1, pulse. Because if I just do it by myself, it's going out to there. All right, and if you do it by yourself. All right, so now 3, 2, 1, pulse. About where shade is. Did it seem like it moved more or less to you? It's supposed to, and that's known as destructive interference. So when the two waves are on opposite sides of each other, they will interfere with each other, make something smaller than what we started with. Now, if we created waves that were the exact same size, or when they met, they were the exact same size, but on opposite sides, then they should have completely canceled each other out at some point, and the middle point should not have moved at all. Now, in reality, our waves will be slightly different, and so it probably is gonna move a little. All right, so now we're still. I send a wave down, it reflects back on the other side. So what happens if I send a second wave? Well, that first wave is still moving. What do you mean by that? I was trying to make it the same size, I just did that. So what happens when I send the first wave down, what happens when it gets to carry? On which side? Okay, and then what's gonna happen when it meets the second wave I send? It's gonna be on this side instead of that side? The second wave I send? Or the reflection? If I send a wave like that, even if I do it a second time, it should still return on the opposite side. It's more concerned, I send one wave down, it hits her hand, it comes back, reflects back on the opposite side. If I send a second wave down, I would still send it down on the same side, so it's basically this. What happens when the second wave I send meets the first wave that's being reflected back?
They come towards there. They come towards there.
They could, they'll talk about when the second one after after the first one's gotten to carry this on the way back towards me. I consider it 4. I said the second one before the first one takes it back to me. All right, let's take it piece by piece again. I send the wave down like that. What can you tell me about the reflection? Okay. side, you go to that side. 3, 2, 1, pulse. 3, 2, 1, pulse. What happens when those two waves met?
The both came back to, one came back E, one came back her.
They actually pass through each other. So the one I send goes to her, the one she sends comes to me. But what happens when those two waves meet? Try that again. 3, 2, 1, pulse. So when I send two waves, the first wave goes down, hits Carrie's hand, bounces back on the opposite side. The second wave I send will meet up with the reflection of the first wave. And what should happen? So my second wave has destructive interference with the reflection of the first wave. So instead of sending pulses, if I went back and forth like that, I'm basically sending waves on this side, then I send waves on that side. The reflection is going to come back on the opposite side from which way I sent it, and it will interfere. There'll be moments of constructive interference and moments of destructive interference because I'm now going to both sides. And if I do that at the right frequency, I set up what's known as a standing wave. Notice in the middle, it's not moving very much. And Carrie's hand, it's not moving very much. In theory, it's not moving very much over here. But there are 2 points about where Joanna is and about right here, which are moving a great deal. The points which don't move, ideally at all, are called nodes. The points that move the most are called anti-nodes. So, this right here is known as, well, let's see if I can, the simplest, the academically simplest pattern is sending waves down at the right frequency. About where shade is, we have an anti-node. We have a node at Carrie's hand and a node over here. That's known as the first harmonic. The second harmonic, the one I introduced before, will increase the frequency. Second harmonic. Is that 3 antinodes? That's the third harmonic. Stability there. Doing okay? What is that? Is that 5? That looks like 5. That's the fifth harmonic, because for some reason, one harmonic is beyond my ability to know. I can increase my frequency even more and get an even higher harmonic if I can just hit that right frequency. Yep, go back to 5. Now, this is a situation where I can change the harmonics just by changing the frequency. However, on the left that you're going to do on Friday, you have a set frequency, and you won't be able to change it. So we have a different way of changing it, by changing the speed. So remember that how fast this wave travels depends, or how the wave travels depends on, as I pull this out, it's going to pull the next coil next to it, which pulls the next one next to it, and so on. When I come back, it's going to again pull on the coils. So if I can increase the force which one coil exerts on another one, in other words, increase the tension, we'll start out like this. So I'm going to send a pulse down, sort of have a mental image of how fast that was. And now, let's increase the tension. What's happening to the speed? Yeah. So I can change the tension and change the speed of the wave. And So in the lab on Friday, what you're gonna do is you're gonna change the tension in the string and thereby get different harmonics with a set frequency. And that's basically what's it. All right, set back in. Thank you very much, Harry.
So what we're going to do is sort of represent the harmonics here. So this is two fixed ends. So a fixed end, or fixate ends, so let's actually put the letter in there. Two fixed ends, wherever you have a fixed end, you have a node. So I have a node here, I have a node here, and in the middle, an antinode. This is the typical way of drawing these. What's happening here in the middle is this is vibrating back and forth a great deal through a combination of constructive and destructive interference. In the lab that you're going to do, you're going to see the string vibrating, and it is possible you're not going to actually see it in the middle here, but if you actually stuck your finger in the middle while the string is vibrating, you would definitely feel it, because the string is moving from this position to that position back and forth. So this is the first harmonic. I think that's off screen there, so first harmonic. The second harmonic, supposed to look more symmetrical than that. The third harmonic. So we're basically adding a node and antinode every single time we go up. So when doing analyses with these, we have to identify actually waves, because these are waves that are being sent, and waves have a wavelength. They have a speed, they have a frequency, using some of the vocab we talked about on Monday. So the question is, how many waves is this? What does a full wave look like? Everyone in here has had trig. So if you think about, if you plotted a sine curve or a cosine curve, I don't care which one. Let's do a cosine curve. If I ask you to draw a cosine curve, hopefully there's one of you that can do this on the spot. How would you suggest I draw it? Sine curve? Would that be better?
The sine curve starts off going through the origin.
Okay, I'm there.
And then it just goes up to the top, and then it just repeats.
Okay. At what point would you say I've done a sine curve?
Just one cycle, yeah.
Like that? Okay, and that's generally what we're talking about when we talk about a wave. It's basically, you start at some point and going in some direction, and you end at the same point going in the same direction. So this would be one wave. Or if we're dealing with a harmonic or a standing wave, we would actually draw it like that. That's one wave. For a cosine curve, cosine looks like that. That would be one wave. Or if we drew it as a standing wave, draw it like that. So one wave. So, how many waves is this? So if I say that the distance between my two ends is L, so let that be the length, L is equal to a half of a wave, or therefore half a wavelength. Or multiplying both sides by 2, the wavelength would just be 2 times whatever that distance is. How many waves is this?
1.
So L is equal to the wavelength. How many waves is this?
1.5.
So L is equal to 3/2 of a wavelength. Or the wavelength is equal to 2/3 of the length. In other words, the wavelength, that's the wavelength right there. Notice every single time we go to the next harmonic, we are adding half a wave. So that's the essence of Friday's lab. Now let's take a look at a couple other examples. So that's the two fixed ends. Let's do, we'll do two free ends. So a fixed end is a node. A free end would be,
One node.
no, not for free. Fixed end is a node, a free end is,
Half width.
I'm looking for the vocabulary word, hoping people would just pick out the fact that it's the other one, it's the antinode. So the simplest one with two free ends basically looks like that. That's the standing wave with two free ends. This distance here is L. The question is, how many waves is this?
Zero.
No, it still counts as part of a wave.
The half?
It is indeed a half. Basically, this is a full wave right here. All we've done is we've taken off the first and last quarter. So that's a half of a wave. So the wavelength is equal to 2 times L. Matter of fact, the exact same thing there. The one fixed, one free is not going to follow that pattern. The next simplest one. How many waves is that? Yep. And how many now?
Two.
Not two.
32, 1.5.
Yes. We have the wave, basically, that's the wave right there, and then we've got another setup. Again, we're adding a half wave every single time. So the wavelength is equal to 2/3 L. Now the two fixed ends, we did that in the hallway. Hopefully you have some visualization of what something vibrating with two fixed ends looks like. But two free ends, what does that look like? Well, we can't really visualize it particularly well. If we had a nice frictionless surface out there, we could put both ends on rods, on frictionless rods, since we're doing fantasy there, put a little pluck on it, and then send waves in both directions, and potentially we could have created it. But more easily, at least sense, with a child's toy. This is what two free ends sounds like. That is the second harmonic. Third, fourth, and then the fifth one's in there. The first harmonic, there's the first harmonic right there. We'll talk about that in a little bit more detail in a moment. Now next one. We've done two fixed, two free. Let's do one fixed, one free. One fixed, one free. So a fixed end is going to be node or antinode. The free end. So the simplest one I can do basically looks like that. So I've got my node over here, I have my antinode over here. This is the first harmonic. How many waves is that? This distance here is L.
Quarter.
Yes. So L is equal to 1/4 of a wave. The wave is equal to 4 times L. The next simplest one, again, I have to have a node at one end and an antinode at the other. How many waves is that?
1.5,
Not 1.5.
3/4.
Three
Yep.
waves.
3/4 of a wave. Again, this is the full wave right here, and all we've done is just cut off that last little bit, that last quarter. So we have 3/4 of a wave, or the wave length is 4/3 times whatever that length is. And look, since now, there's a number of videos and probably some text where I call this the second harmonic. I think the general agreement is this is called the third harmonic, because it's 3 times that one. The second harmonic doesn't really exist, and so it's always a multiple. It's the multiple of the basic one right here. So this is technically the third harmonic, although if you look at old tests, I call it the second harmonic. And I'm gonna have to eventually go through and clean all that up. So the next harmonic, I guess officially the 5th, or what I used to call the 3rd, and how many waves is that?
One and a fourth.
1 1/4. Again, each of these little bits right here is a quarter. Just like that's a quarter right there. So we have a full wave to here, and then a quarter. So this is 5/4 lambda, or lambda is 4/5 of L. Notice that I'm still adding a half wave every single time, just like I did for the other 2 cases. Whatever I started with, I add a half wave every single time. Now, what does one fixed, one free end look like? Well, it looks like this. So let's go through and make a prediction. I have a tuning fork which will vibrate at 256 hertz. I'm assuming your hearing is better than mine. Can you hear that? I guess you're the farthest away. You can hear it?
I heard like a ding.
Okay. That one's a little bit better. Now, whenever you're using a tuning fork, please don't bang something hard on it. Even though you get a really nice sound if you do that, banging on something that's soft. If you look at some of the older ones we have, there are dings and nicks all throughout it just because people banging metal on metal. It will happen occasionally, but try to minimize that. So that's why, actually, flesh works a little bit better as long as you don't hit it in the wrong spot. Now, if I put it over this, basically this tuning fork is now vibrating back and forth at a certain rate, creating these pressure waves going out. The waves, within one period, however much time it takes to go back and forth, within one period, the wave's going to travel a certain distance. It's going to bounce up against the surface here and then bounce back. This would be a node. When we hit the harmonic, that's a node, and this is the antinode. Now recognize that the antinode is when it's swinging, when you have the biggest variation in pressure, which means it's going to push your eardrum in and pull it out the farthest. So this will be the loudest sound when you hit the harmonic. And we can predict how tall this column needs to be in order to hear it. And this is the point I get overconfident because I did this last night and it actually came out rather well. So I'm assuming it will work again. On Monday, did we do speed of the wave formula? I think I wrote it up briefly when I talked about F versus nu. Or did I talk about F versus nu? I did, okay. Did I derive the speed formula there?
I don't think so.
Okay.
Oh, actually, I think you did. It's the wavelength times the frequency.
Yes.
Yeah.
Okay. So the speed of the wave is going to be the frequency times the wavelength. There's another formula that we will use on Friday and equate it to this. So the tuning fork has 256 printed on here. So the frequency of this tuning fork is 256 hertz. the speed of the wave, I'm not talking about how fast this thing's vibrating, I'm talking about the speed of the wave that's produced, basically the speed of sound, is roughly 340 meters per second. It is dependent upon the temperature, so it's not an exact number, but we'll go with it. So 340 meters per second, plugging into that formula, is equal to the frequency, 256 hertz, times the wavelength. There we go. So the math problem is 340 equals 256 times lambda, divided by 256. It's off to the side for just a moment. Hopefully not knock it down. So what is the wavelength that is produced by this tuning fork?
1.33.
Meters per second and hertz.
That is true. We can simplify it some. That would be a meter per second hertz. But we can simplify it one step further. What is a hertz anyway?
The cycle over the time?
Yeah, so it's more specifically for hertz, it's cycles per second. So a second hertz there, those cancel each other out. So we're left with meters. So 1.33 meters. We're also finding a wavelength. It is a length. It is a physical distance, 1.33 meters. So based on what we have over here, the length of my air column, where I get a node at one end and an antinode at the other end, well, that length should be a quarter of the wavelength. And so given that that tuning fork is giving us 1.33 meters, the length would be 1/4 of that, or about 0.33 meters. And then a quarter of that is going to put it somewhere around 0.33 meters, give or take.
I had 1.328125.
Okay. And then when you take, a quarter of that, and it rounds off to 0.33. What is it? Let's go out one more decimal place.
0.3320.
Sorry. So, what I'm claiming is that it should be louder when the air column here is 0.3320 meters tall. Now, that level of precision is a little bit beyond what I can do right now. But let's talk about, we've got this metric, we have centimeters listed on the side here. We have 0 at this point right here, that's 2 centimeters from the top. I don't know why, but they were consistent with it. So 2 centimeters from the top. So 0.33 meters, or 33 centimeters, should happen here at the 31, because you got the 31 centimeters to there, plus the extra 2 centimeters. So we should have it loudest somewhere around there. Let's bring in some chapter 13 stuff. We have water in this reservoir right here and water right here. The level here and here are the same thing, are the same. So if I lift this up, this will move up till it's at the same level as the water in the reservoir. Or if I bring it down, this should be dropping and this will be going up, and they'll move until they're at the same level. And I don't know if it's one of the questions from the 11 through 14 homework quiz, because it might have been an odd problem, but that answers one of those questions. So these are at the same level. If you were skeptical, you can come up and take a look, or just trust it for now. Air pressure is the same on both sides. All right, so I'm going to raise the water in the tube here just by lifting this, and we'll get the tuning fork situated. I want to get it closer to it because I want as much safe as possible. And I need something to bang it on, or to bang it. There's that louder there. At least I hear it louder, I assume you can. So that's the first harmonic right there. The second harmonic should be 3 times that. So the second harmonic should happen somewhere about 0.99 meters. And this is the point, if I'm not careful, I'm going to spill water everywhere again. Don't want that in waiting. So 0.99 puts it somewhere around, let's see, plus the 2 centimeters at the top, should be right there. Let's see how close we get. There we go. Let's stop that, get this thing that again. Very close. And then fades off. But it's a lot closer there because we're getting the next harmonic. It's the next time that we have an antinode right here at the top. And again, antinode get the largest vibrations, which means the loudest sound. So once more, physics demonstration that actually worked. It's nice when that happens. Questions to hear? Talk a little bit more about sound here. There we go. I assume everyone can hear that. That's 440 hertz. That's 439.5 hertz. We play them in a little bit quicker succession. .440 hertz, 439.5. Now some people have sensitive enough ears they can tell the difference. I am just curious, is anyone in here can tell the difference between those two? All right, so how can we actually tell if there is a difference? Maybe I'm just making stuff up. Well, we have a way. Remember we talked about interference in the hallway, constructive and destructive interference. So if I have one wave that is playing with a certain frequency, and I play another wave with a slightly different frequency, so these waves are closer together here. Notice there are places if you play them at the same time, at times that they will peak at the same time, times will trough at the same time. So, and sometimes they'll be in opposites. So these are sort of opposites right here. We're going to get some destructive interference because this one's going down while this one's going up. We'll have other places where we have constructive interference because they're both going down at the same time or up at the same time. And so you should get these cycles where sort of oscillating back before with higher and constructive and destructive interference. So I'm going to show you two waves. And I forget what the frequency is there, but there's a particular wave there in purple, oscillating back and forth. So I just basically, it's a sine wave that I printed out. And I have another one right here. So notice that these are not exactly the same, even though they look very similar at a quick glance. They both start at 0 over here and here. But they get to a certain point where this one ends just after bottoming out, and this one ends on the way down. So they are slightly different. Again, I'm trusting that you can see it, or if not, you will. If you need to see it closer, I'll be glad to bring it over to you. Now, in order to be able to look at the overlay there, I basically took the blue one here and I traced it onto this transparency. And so the transparency should, for the most part, be matching exactly what's underneath it. Looks like I did a much better job here than I did over here, but I think that's close enough. So this transparency is just a tracing of the blue. I'll bring the purple, start them off at the same place. So I have the purple one here that is now basically lined up with the blue one. They start off at the same, so we have constructive interference there. It is actually constructive all the way through, but I'll show that in just a second. And then you start seeing it getting slightly out of sync here, and then much farther out of sync by the time you get to the end. So there's two little peaks right there, whereas here it looks kind of like one. And then I added them together. If you add them together, you get this. You start out with a peak. Both of these have an amplitude of 1. When you add them together, the sum has an amplitude of 2 right there, goes up to 2, and then that amplitude gets smaller as we go. Because you start getting, it's still constructive interference by the time you get to here, but you can see that the trend at some point is to become destructive. And so if you expand farther, you get this. So what I just showed you goes out to about there. That's basically what I just showed you was out to here, and I went ahead and took it farther. So you notice you have this, it starts narrowing down to this point, that's complete destructive interference, and then it starts to build up again. So this is louder than either sound individually, and this is incredibly quiet. So if I play two frequencies that are very close to each other, you should hear a pattern like that. And let's do it. 439.5, 440. Stopping the 440, it goes back to sounding like a single tone. I add in the 440. So let's make a prediction. When they combine like that, this is what's known as a beat. And they have a beat frequency. Beat, B-E-A-T. The most sophisticated math you will ever see, we're about to do. The frequency of one of them was 440 hertz. The frequency of the other one was 439.5 hertz. The beat frequency. Get ready for it. Subtract 0.5. That's the beat frequency. Perhaps not the most sophisticated math you've ever seen. Now, was what we were hearing just then when I played both of them demonstrating a beat frequency of 0.5 hertz? Well, let's translate that into a time. If the beat frequency is 0.5 hertz, what is the period? What is the really? Sorry?
100.5?
Yep. Which is 2 seconds. So we should hear it get really quiet every 2 seconds. And we can test that out. One 1001, 1002, 1001, 1002, 1001, 1002. So it indeed does seem to be matching exactly what was predicted. If I went to 438 hertz and 440 hertz, what would you expect the beat frequency to be? That's 440 and 438.
Two.
2 hertz. And what would be the period? Okay? Every half second. So I would expect this to be a much more rapid oscillation here. Here's 438, 440. Now, as they get farther and farther apart, it gets a lot harder. So if I did 400 and 440, you get a trill in there. That's 40 hertz off. If I went 300 and 440, that's 300. At that point, to me, it just sounds like two different sounds playing. You're not getting that trill because at some point we can't process it. But we now have a way of actually testing frequencies. Thus enter the red tube. Questions to hear? All right, so assuming the speed of sound is about 340 meters per second, so V is 340 meters per second. L is going to be the length of the tube, because we got the two free ends right here. And the length, now as I swing it around, it is going to stretch a little bit, so I'm just going to add a little bit of a stretch as I do this, start easier on that other end. And I'm getting 79.9 centimeters. So L, 79.9 centimeters, or 0.799 meters. The first harmonic happens when the wavelength is twice that. Let's call it lambdas of 1, and I know there's a black marker around here somewhere where that writes better than that. Yeah, there we go. So lambda sub 1 is 2 times L, or 2 times 0.799 meters. Okay. Meters. So the frequency we should hear for the first harmonic, well, I know that V is equal to the frequency times the wavelength, or the frequency is equal to the speed divided by the wavelength. So that'll be 340 divided by 1.598. So what is the frequency of the first harmonic? Units?
Meters.
Frequency.
Hertz?
Yes, that's a meter per second, and that's a meter. The meters cancel out. You're left with 1 over seconds, which is a hertz. So 212 points. I'm going to round off to 8 in terms of the machine here. This is what that sounds like. 212.8. All right. So as I swing this, the traditional part of this part of the show is my excuses. We found this in our backyard in the first house we owned. There was this one section of the yard that was covered in ivy. Found a barbell set, found this, and I still half think there was a dead body in there somewhere, but the houses we afford on the first time. Did I talk about the gunshots? So our first house, it was a Saturday morning. I was taking my son to the library as we usually did, and I step outside and I hear this pow, 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 followed by the squeal of tires. And I say, let's go back inside for a bit. And about a minute later, I hear police sirens. Yeah, that's the neighborhood we were living in. So, anyway, that's what part of the reason I expect a dead body somewhere in there. But anyway, we found it outside. It's been crushed. Who knows how old this thing is. So they're my excuses. All right, so here we go. Oh, the other excuse is this is physics demonstration, so good luck. So as I swing this, the tip here is traveling faster than down here, which means the air up here is going to be pulled along, and so the air up here is traveling faster than the air down here. And since the air is traveling faster, we have a drop in pressure. And because there's less pressure at the top here, air is going to get sucked up through the tube. Now, the ribs on this are to get the air to vibrate. You can do it with a smooth tube, but you don't get the nice sounds. It's more of a different frequencies of whoosh. So the first harmonic, really, I can't swing this fast enough to get enough air flow through it. So the first harmonic, we really can't hear. Or perhaps you can, and I've nailed it. That sounds like the same thing we had over there. So I get a little bit faster. That's actually the second harmonic. So let's make that prediction. So the second harmonic, the length is equal to the wavelength. So that's equal to L. So that's going to be I can do that math in my head, 0.799 meters. So the second harmonic, the frequency of the second harmonic, is the speed divided by wavelength still, which is 340 divided by 0.799.
Four 25.
25, okay. Oh, yeah. The rest of it okay?
Mm-hmm.
Okay. It should have just been twice what that if that was. Hertz?
19.
The 19? Oh, rounding. Okay. So this is what that second harmonic should sound like. 425 point. Let's assume. Let's just be ambitious, type it all in. So with that in mind, it sounds similar. The tone's a little bit different just because we have speaker versus broken tube or plastic tube. But we can get some sense of whether they're even close to each other by playing them at the same time to see if we hear that trill of the beats. Just can't do it that way. There's an extra trill in there that I'm definitely hearing here. Are you hearing the trill? So we're close enough at least to be hearing a trill, so we're probably not too far off in our prediction. It's going to get harder as we go, but let's do the next harmonic. Next harmonic, the wavelength is 2/3 the length. or something.
And we have point six,
Wait, six, oh,
point six, 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 and then seven at the end.
sorry, I guess 6 repeating.
Yeah.
Right. So, the frequency of the third harmonic will be 340 divided by 0.66 and so on. No, something's off.
Point six six, repeating is 2/3.
Oh, yeah, times
Decimal 2/3.
times 0.799.
Like 5.26.
0.5,
326.
0.5326, okay. Give myself more room there. First. Right. So to give you an idea of what we're predicting, second harmonic, that's the third harmonic. Yeah, third. Let's see how close we get. So 638.4. I think we'll all agree that's exactly the sound that was just played to this thing. The trill is a little bit harder to detect, but there is just a little bit of a trill there. We're a little bit farther off, instead of shouting over that, a little bit farther off than we were for the prediction for the second harmonic, but to me there's enough of a trill there to at least indicate that we're, probably within 20 hertz or so. So some evidence at least to support some of the stuff we're talking about right now. And you know what, there's one other bit that probably would be nice to talk about, but I can do that at the beginning of the lab. One other bit that's necessary for the lab, but I'll talk about that on Friday.